Hey guys, going to try to make it where there's only one video on chapter 1, and I think I can do it. It may be a long video, and then it may not. I don't know how this will play out. But tell you, number one, I'm not a big fan of PowerPoint. In fact, I won't use PowerPoint very often throughout the semester, but this is one place where I think that it was appropriate to use it. So, hey, let's get going. What we're going to talk about here will be different types of data, collecting data, different samples and populations and things like that. So, guys, take good notes when you go to do your first homework assignment. Technically, your second homework assignment, because your first homework assignment is to make contact with me via email. But you should have seen that in the introductory video. Anyway, take good notes because it's going to help you do really well on the first assignment on my math lab. I'm about to lose my voice, so I may not even finish this. What is statistics? Statistics is the science of collecting, organizing, and analyzing data. I promise you I'm not going to read the PowerPoint, all the slides to you. When I see this definition, I think of a time I was teaching this class at the University of Kentucky quite a few years ago, and I required my students to do a project. Well, long story short, there was one particular student who wanted to, that year Kentucky played in the final game. Actually, we won the NCAA championship that year in basketball, and she wanted to know the percentage of students at the University of Kentucky who watched the final game, watched the championship game. Now, there's 25,000 students there, so there's no way that she could go out and ask everyone, which is typically the way in statistics. So she was going to choose a sample, hopefully a random sample, and use the sample data to generalize to the larger population. Something we do in statistics all the time, and something I'm going to teach you throughout this course. So she comes back a couple of weeks later with a confused look on her face, and she says, wow, I sampled, I forget how many she sampled, somewhere around 100 to 200. And she said I think it was 100, now that I think about it. She said every single person that I asked said they watched the final game. Well, I found that really hard to believe because, trust me, from spending a lot of time in the library at the University of Kentucky, I know that there are a lot of, well, I don't know about a lot, but there are some students at the University of Kentucky that don't even know that Kentucky's got a basketball team. So I prodded a little more. I said, well, tell me how you collected your data. And she said, well, I thought I'd have some fun with it. And I'm like, well, that's good. I like to have fun. And she said when she went out Saturday night with her friend, she decided that she would ask people at the bar. I said, okay, what kind of bar did you go to? And she told me the name of the bar. Essentially, it's a sports bar located on the campus of the University of Kentucky. So anyway, any data that she collected, because her collection process, her collection procedure was so bad that anything she did in terms of organizing and analyzing her data was completely irrelevant and totally meaningless because of the way she had collected her data. So we don't spend a lot of time in this class talking about different sampling techniques and ways to collect data, but we do talk a little bit about it a little bit. But in terms of organizing and analyzing data is what we focus on mostly in this class. Why do we care? Well, first of all, from a very pragmatic perspective, you care because statistics is needed for you to complete your degree. But in a more meaningful perspective, why do we care about learning statistics? Well, first of all, you're going to be surprised how many of your majors require at least some fundamental understanding of statistics. Secondly, it makes you cooler, right? Okay, maybe not. But no, seriously, it tells you more about the world around you. For example, presidential election going on, you see all these results about surveys and polls and margin of error and different things like that. You're going to understand a lot more. And Understanding more about statistics helps you understand more, but it helps you point out when people are using statistics incorrectly. There's a book that I used to require my students to read. It's called How to Lie with Statistics. In fact, there may be two editions of that now, but I'm not really sure. You can do all sorts of statistical trickery to deceive statistical results. Well, first of all, I want you not really to learn those procedures so you can trick people, but I want you to learn procedures where you can point them out and detect them when people are trying to use them on you or the general public. Guys, two major concepts, at least this perspective, data and variation. Let's think about some exam scores. If you look at those four data sets, the first one 80, 80, 80, the second one 79, 80, 81, and so on and so forth, the average of all those data sets is 80. So if you can think about having a class of 3 students, class number 1 scored 80, 80, 80, average of 80. Class number 2, 3 students in that class, 79, 80, 81, average of 80. The same thing with the third class. I don't know really how you'd score a 240 on an exam, but let's say it was a 250-point exam, whatever. I'm stretching here, so cut me a little slack here. But anyway, all 4 of those have an average of 80, but when you look at the variations aren't comparable. For example, 80, 80, 80, there's no variation whatsoever. 79, 80, 81, there's more variation there than there is in the first 3 numbers, but there's not as much variation as there is from 70, 80 to 90. So guys, variation is a very important focus on learning statistics. So many of my students come to me. I've taught this class, I'm pretty sure it's over 100 times. So many students come to me and they know about averages and they know about means and possibly even median. But they don't realize that the most important thing to focus on in an introductory statistics class is variation. Sorry, I'm getting distracted, but for some reason my my Apple Watch is picking up my lecture, which is just really crazy. Okay. We also see variation in just the ways that we write things. For example, I put down 4 Z's there. All of those look different, right? They're all Z's, but they clearly vary in the style of Z. So, guys, we see variation all the time. Drive down the road. Cars look different. Trees look different. Cows look different. Horses look different. People look different. All kinds of variation. And in statistics, we're interested in how do we describe variation within a data set. So remember, context is the key. If I give you 4 numbers, 8.32, 7.91, those 4 numbers that I give you, they take on completely different context depending on what they're measuring. Birth weight would be one thing. Millions of people would be something different. So guys, always remember that it's not just about the numerical. It's just not about the number. It's just all about that number you see. What's important is what those numbers stand for in terms of us telling a story with statistics about the data that we've collected. Data sources. This is one of the key screens, key slides of this PowerPoint. Think of a population as the broader, larger group of people, subjects, cats, dogs, trees, animals, whatever it may be, that you want to generalize to. Typically, we study populations that have information that's difficult to obtain because there's just so many people or subjects and elements, dogs, cats, trees in our population. And what we do is we go in and we collect a sample, which is a subset of the population, and analyze it with the purpose of generalizing from the sample to the larger population. We do that because if If we do a good job of collecting our sample randomly, then it's reasonable to assume that the characteristics of our sample will match pretty closely to the characteristics of the population from which it was drawn. Now, there's always error, there's always deviation. You collect a sample, 2 seconds later you collect another sample from the same population. Well, your samples are going to look different. There's going to be some variation even within samples collected from the same population. So, guys, again, variation, variation, variation. It's all about variation in statistics, even when we're talking about samples. But guys, typically, if we want to investigate a characteristic of a larger population, maybe the all registered voters in the United States, it would be completely impossible to go out and obtain information on all the voters. So we would take a sample. And if we collect a random sample, a good sample, then it's reasonable for us to assume that the characteristics of that sample will match pretty closely to the characteristics of the population. In fact, that's one of the things that we assume to be true. So, an example, suppose you want to know for what presidential candidate, A, B, or C, students at SSU prefer. So we survey a random sample of 500 SSU students and ask them their presidential candidate preference. So who is the population, who is the sample, and what data was collected? Well, guys, the answers: your population would be all SSU students. The sample would be the 500 students that you sampled. And the data that was collected would be the presidential preference, A, B, or C, Clinton, Trump, or Bernie. So guys, the goal, collect a random sample from a larger population with the intent of generalizing. So in other words, what percentage of cars in the U.S. are white? Answer, I don't know. Statistics is your best friend. You go out, you collect a random sample, and use this sample as an estimate of the larger percentage of cars in the United States that are white, which would be impossible to attain through a sample. So first of all, a variable, just from the simplest, the basic definition means that it's something that varies. And in this class, we're going to collect variables as characteristics of people or things. And there's going to be two types of variables that we're going to focus on. The first variable is called categorical. That is also called qualitative, a qualitative variable. And it describes a quality or a class. It can be numbers, but no arithmetic is possible. Hair color, zip code, letter of the alphabet, gender, political preference, religious affiliation. Those are all things that we could assign numbers to, like gender. We could assign gender zeros and ones as male and female. But when you add them together, the arithmetic means has no meaningful interpretation. I should have said letter grade. The second type of variable we're going to talk about is numerical. And guys, we call that a quantitative variable, and it describes a quantity or a measurement. That's a numerical variable is data that is collected on a person or a thing, where the quantity that you collect in your sample means something. You know, your height, your ACT, your GPA, the number of cars you own, you know, the number of boyfriends or girlfriends you've had in your life. That is a quantity, a measurement where arithmetic actually does mean something. So let's go through an example. Let's say that we want to collect some information on students at Shawnee State. So the first thing I may ask them is their name and maybe gender, male or female. I may ask them their age in years. I may ask them their age in terms of a classification, Let's say we classify 1 to be 17 years and younger, 2 to be 18 years old, and 3 to be 19 years and older. Maybe we ask them their ACT, possibly their high school GPA, and the state in which they attended high school, and well, let's say the state in which they graduated high school. So we'll code 0 as Ohio, and 1 is a state other than Ohio. So guys, if we go through these, we can see that name would be categorical qualitative, gender would be categorical qualitative, your age in years would be numerical because it would be a number, but your age classified as a category, 1, 2, or 3 in this situation, would be categorical or qualitative. So, you know, a lot of times we do age groups like I've done here. Sometimes we do that with income, right? What's your annual income? Well, you know, somebody says it's $32,865. But sometimes we do income groups, 0 to 50,000, 50,000 to 100,000. So just because something is naturally numerical doesn't necessarily mean that it's been coded numerically. It could be coded categorically. ACT would be something probably would be numerical quantitative, high school GPA the same, and the state in which the person received their high school diploma would be clearly categorical, zeros and ones. Guys, when we have something zeros and ones, we call that dichotomous. So so the way we have this survey set up, state would be dichotomous, but age would not be because it has 3 classifications. Now, let's collect some data and see how this all plays out in the real world in statistics, okay? First of all, student walks in. His name is Frank Lieberg. He's a male. He's 19 years old. His age classification would be a 3 because he's 19 or older. Let's say he had an ACT of 22, a high school GPA of 3.4, and he lived in Kentucky. So we would code him as a 1 for state because it's something other than Ohio. Now, I don't know a Frank Lieberg, and I just made this up. So if you do know a Frank Lieberg from Kentucky, don't take this literally. And don't tell him I used his name either. Mary Smith, that's a pretty common name. Female, 18 years old. Age classification would be a 2, ACT 28, a really big old GPA at 3.92, and apparently Mary graduated from high school in Ohio. Now, we could do that for more students, and let's say we did that. So you can see that Frank and Mary are coded there, and we have their gender, their age, their ACT, and their age classification, their ACT, high school GPA, and state. Now guys, this is called a spreadsheet approach. This is called a stacked approach at organizing our data. To me, this is the most preferred because the statistical software package that I'm going to teach you, this is a really clever way to get our data set from a spreadsheet, like an Excel spreadsheet, into R, the statistical software package, and analyze the data. So this is my preferred way to organize data. So at the end of the day, we can say that we have 7 cases or observations. Now, research has shown when people with no statistical background looks at a data set like this, they read left to right because that gives the juicy gossip. For example, we look down there to Nancy, who's our 6th person. Well, Nancy's a female. Nancy's 22 years old. Her age classification's a 3. She had an ACT of 20, a high school GPA of 3.25, and her state is coded as 0, which tells me she's from Ohio. But when someone like me, with a statistics background, when I look at that, I don't read left to right. I read up and down. And if I do my job correctly in this class, which I will, I promise you, I'll do my job correctly. If you do your job correctly as a student, when you leave this class, you're not going to care much about left or right. You're going to care about up and down. So when I see a data set like this, my first thought is, let's talk about gender. Well, what percentage are males? What percentage are females? Let's talk about age. What's my average age? What's my median age? What's the standard deviation? How much variability? I look at age category. Well, what percentage are in category 1? What percentage are in category 2? What percentage are in category 3? ACT is quantitative. I would think about average, standard deviation. High school GPA, quantitative. I would think about average, standard deviation, some other things I'll teach you. I look at state, it's categorical. What am I going to think about? Counts and percentages. So the game plan for us describing the variables in our data set, which are up and down, gender, age classification, ACT, high school GPA, and state, those things up and down are our variables. The way we classify our variables depends on the type of variable that we have. If we have categorical, gender, age classification, and state, then we have one approach to summarizing the data. If we have quantitative data like age, ACT, and high school GPA, then we have another approach at summarizing that particular type of variable. So guys, that's all to be learned. That's what I get paid the big bucks for, is to teach you this stuff. But it's important to know when we've got a data set like this, cases and observations go left or right, and you can see that we have 7 people included, and variables go up and down. Now, there may be a good argument to say we have 7 variables, that name could be one of the variables. And if you want to go there, that's fine, but I typically don't include name as one of the variables. Okay, storing data, which is stacked. So stacked data looks like a spreadsheet format. That's what we just looked at. It can store many variables, and each row contains information on a single variable. So the very first line, I know that that person, their weight is 7.69 something. Female, I'm assuming that 1 stands for, well, I don't know. I'd have to look at the legend. And smoke, I assume that's probably yes or no. But again, that would have to be explained. And I'm kind of glad it played out like this, because data that we collect, guys, has to have a context. Now you can see down at the bottom, you can see that the variables are birth weight, gender, and smoking status of the mother. But we don't know what zeros and ones. We don't know whether 0 is yes and 1 is no, or vice versa. Typically, no stands for 0 and yes stands for 1. But we would need to know that before we could get into this too heavily. Unstacked data, and from time to time you'll see it like this, where you'll have the men's heights in one column and women's heights in another. What you have to understand here is when you read left to right, that 70 and the 59, which are on the first row, have nothing to do with each other. So each column is a variable from a different group, but the information in the row does not correspond to the same individual. You know, I collect data that way. I organize data that way sometimes, but I prefer the spreadsheet and the stacked way of storing data typically. Okay. So organizing categorical data. Why organizing is important, and I want to give you an example of a two-way table. So why do we need to organize data? First of all, raw data can be extremely messy. When I was in grad school, we had a data set that had about 20,000 cases, over 12,000. No, I'm sorry, it had more than 20,000. It had, no, I'll take that back. It had over 20,000 cases or individuals or subjects over about 1,200 variables. It was called NELS, a National Educational Longitudinal Study. Even when it was organized and collected in stacked format, it was still hard to read. But if the numbers had been just everywhere, you can only imagine how messy it would be, and how it would be really hard to detect certain patterns in our data set. So guys, organization is extremely important. Now, when we have two categorical variables, it's often important, or at least helpful, to organize our data in a two-way table, and I want to show you how that plays out. So let's say that we've got some data that we've collected. It's in stacked format, so the ID 1 tells me that that person is a male, and that person always wears their seatbelt. The second person is female, and they don't always wear their seatbelt. Guys, trust me, the statistics shows you should always wear your seatbelt. Now, I want to talk about that later. You get into some anecdotal evidence there where you know someone who unfortunately died in a car accident because they had their seatbelt on and they were trapped. Well, that stuff does happen. Statistics doesn't always speak for everyone. We speak for general, typical patterns. But there are certain observations that don't necessarily follow suit with the patterns that we observe. But we'll talk about that in just a second. It falls under what I call anecdotal evidence. So anyway, when I look at this, I know I've got some males and females, and I know that some of them wear a seatbelt and some don't. But if I wanted to investigate this further to see if there's any relationship between gender and seatbelt, well, I might want to put this information in a two-way table, which I did. So my variables here are gender. That's on my columns. And the rows here represent the seatbelt status, either not always or always. Now, once I break it down like this, I can see that two males in my sample not always wear their seatbelt, but three males always wear their seatbelt. For females, you can see that 3 don't always wear, but 7 always wear. So I can also get a very quick total. I can see that I have 5 males by adding the 2 plus 3. I see that I have 10 females. Now if I'll add the rows of not always, I'll see that 5 people in this data set don't always wear a seatbelt, but 10, the 3 plus 7, always wear their seatbelt. So by doing something as simple, I mean, I have 2 12-year-old daughters. They're in the 6th grade, and they're actually pretty smart. But, I mean, this is something that they could even do. It's not high-level mathematics making a two-way table. Sometimes it just takes a little work. And I'll show you a way in R that it turns out to be really, really, really easy to do. But anyway, a two-way table just organizes your data, and it allows you to see patterns, whereas from the previous screen, we may not have seen those same patterns. Now, we can even dive into this and make some more statements. We can see that 10 out of 15 are female, so 66.7% of my sample is female. I can see that 5 out of 15 are male, so 33.3, or a third of my sample are male. I can see on the top line that I have 5 total participants who don't always wear their seatbelts, and 3 of those are female. So 3 out of 5, or 60%, who reported not always wearing their seatbelt were female. Now, if I come down to the always line, I can see that 7 of the 10, because again, 3 males and 7 females give me a 10 total. So 7 of the total, 7 out of 10 of the females, well, actually, I'm going up and down here. If I look at the female column, so 7 out of 10 reported that they always wear their seatbelt. So we could look at other things as well, but those are just 4 that I picked out that I thought were kind of interesting, or at least, I don't know about interesting, but kind of something. Guys, don't get impulsive. Sometimes we look at numbers and we think we make quick conclusions without really thinking. So given the data in the following table, which sport listed is the most dangerous? Well, when I look at that, it's so tempting to just assume that maybe we have 100,000 in each and look at the biggest number, which is basketball, and assume that basketball must be the most dangerous because it had the most injuries. So if you answered basketball, it's not correct because we're missing some very, very, very important information. Now, let's go ahead and look at the information that would be nice to have. How many total participants do we have? Well, you can see that in basketball, 500,000, just a little bit over, out of 24 million. So if you come over to the rate of injury per 1,000 participants, it's only 20.54. Football, on the other hand, didn't have as many injuries, but it has quite a few less, almost 5 million less participants. So, but the rate of injury per 1,000 participants is about 50.78. So I guess you could say that it's almost 2.5 times, it being football, is about 2.5 times more dangerous than basketball, but it was misleading when we were just given the number of injuries. So guys, make sure again you put your results in a context. And when you're looking at counts, in this case participants, when you're looking at counts, in this case being injuries, always make sure you know how many participants, out of how many. And the best way to compare things like this is always to look at a percentage or a rate of injury per 1,000 as they have done here. Let's move into conducting a study. We often talk about experimental groups, and typically when you talk about an experimental group, you talk about an experimental versus a control group. Guys, the experimental group is the one that receives the treatment, and the control group is the one that does not receive the treatment. For example, I'm serving on a doctoral dissertation committee right now, on an advisory committee for one of my students, and she is investigating the effects of collaborative learning. So her experimental group is half of the students in this particular program who received their instruction using collaborative learning. The control group is the students who received not via collaborative learning. So they received instruction just like they've done before. So we came up with some measurements to see if the collaborative learning approach is actually effective, and I'll keep you posted on that one. We don't know yet. Hopefully she'll defend sometime soon. Other types of studies, anecdotal evidence. Anecdotal evidence drives statisticians absolutely crazy. Let me give you an example of anecdotal evidence. Guys, overwhelming scientific research, medical research that shows smoking is a contributor to lung cancer. But you can get in an argument with someone that doesn't know much about anything that will say, well, my Uncle Billy is 92 years old, he smoked every day of his life, and he never did get lung cancer. So all the studies that were done by Johns Hopkins and Harvard and Yale and all these very, very, very established organizations, this guy will completely throw out all those studies based on one person's story. Guys, statistics doesn't care about one particular person. Statistics cares about relationships between variables. It cares about patterns. It cares about summary statements based on a group of people. There are always anecdotal evidence that will dispute statistical evidence. That's not what we're in the business of, guys. We're not in the business of anecdotal evidence. We're in the business of conducting well-planned statistical studies that come in and look at patterns and make summary statements based on those patterns. It doesn't mean anecdotal evidence is bad. For example, I know someone that was interested a few years ago in telling a story what it was like to be the first African American law student at the University of Kentucky. Well, you couldn't carry out a statistical study there because you only had one person. And we have to have variation. We have to have more than one person to have variation. So statistics wasn't appropriate. But this person came in and did what's called a qualitative study, kind of an anecdotal study, if you will, and told a story based on that particular person's experiences. It was a very neat read, I'll tell you. But so anecdotal evidence isn't always bad. Anecdotal evidence, storytelling and stuff can be very, very, very powerful and very meaningful and appropriate and worthwhile. But anecdotal evidence, in the term of telling one particular person's story that contradicts years and years of statistical data, is something that drives statisticians like me absolutely insane. Observational study, subjects placed into different groups by choice or someone else. This is typically where you would talk about a control experimental study. But what you typically do in an observational study is you observe some behavior that's not really part of an experiment. You just sit back and observe what happens and report it and talk about the patterns and so on and so forth. We run into confounding variables a lot, and any variable that kind of lurks, it's in the background, it hasn't been accounted for, but it has plays a huge impact in explaining the difference in the groups that are being studied is called a confounding variable. For example, let's say we did a study where X is the number of hours exercising and Y is the number of pounds gained or lost. We crunch our data, and this particular study finds out that as the number of hours of exercise increases, that the number of pounds gained increases. Well, how could this be? Well, there's clearly something else that explaining that relationship, and very likely that extra thing could be the number of calories consumed daily. So any variable that's not being accounted for, but it has a way of explaining a difference in the outcome is called a confounding variable. So guys, the gold standard in experiments, something super duper duper important to think about when you read the paper or read a journal or professional publication. First of all, look to see if it was a adequate sample size. Now, ideally, we like in statistics to have large samples, but sometimes you can't get a large sample and you're forced to deal with an adequate sample. For example, let's say you get your dream job and you're working for BMW, and you are put in charge of analyzing crash data for this new car that hasn't yet been released to the public. So you can't go back and use historical data. So what you need to do is you need to take some of these prototypes, take them out and crash them, and analyze the crash data. So you were told by your statistics professor like me that you need a large sample, so you go to the CEO and you tell the CEO, hey, dude, I need 75 of those BMW 725s or 735s so I can take them out here and crash them into a tree. Well, you're probably going to lose your job because they're not going to give you 75 of those cars to carry out the crash data. You might get 4, you might get 5. And in that situation, that would have to be adequate because that's all you're getting based on certain constraints. But guys, when we have our opportunity to get larger sample size, typically, or at least sometimes, that's advantageous. Guys, we want our assignment to your treatment or your control group, your treatment or your experimental group, your experimental or control group, to be random and controlled by the researcher. You want to use a placebo if it's applicable, and you want to use a double-blind study. Guys, a double-blind study means that not only do the participants know if they're in a treatment or an experimental or control group, but the person conducting the experiment also doesn't know. I did an experiment study not long ago with success rates in Math 1500. statistics, our introductory statistics class at Shawnee State. And, I teach a lot of those classes, and I taught even more of them back then. I've moved more into the graduate program and doing that. But back then, I used to teach 4 or 5 sections every single semester. Well, I didn't want to know which students were in the control or the experimental group, because I might be tempted to, well, I wouldn't have been, but somebody might say I would have been tempted to do something unethical just to create the results that I wanted or expected. I wouldn't have done that, but nevertheless, for the just for the ethical considerations of your study, a double-blind study is advantageous. So, guys, statistics in the news. Hopefully, by the time you complete this class, when you see it everywhere. Not only is this something that you may encounter in your major, something you may encounter in scientific research, but you see statistics everywhere. You see it in the news all the time. So things you should ask yourself, is it an observational study or a controlled experiment? Did it meet the gold standard? Was the paper published in a reputable peer-reviewed journal? And did the study follow people for a long time? Well, guys, that's all I've got. That ends this video. Again, I'm not a big fan of PowerPoint, but this was a situation where I thought PowerPoint was appropriate. The next thing I'll do is I'll put up a video where I show you how to use R, which is our statistical software package, to do some of this, create these two-way tables and things that we talked about in this video. So, guys, take care. Oh, I'm not done. Thought I was done. My math lab assignment due soon. Again, perks to getting assignments submitted by the due date. You get bonus 10% on your assignment average in the end. And if your midterm exam score is less than your final exam score, you get to replace the lower midterm exam score with the higher final exam score. Guys, I'm done. Bye.